So, hyperbolas, first glance, what do you notice? There's two focuses, just like we have with ellipses, right? What do they kind of look like? Sorry. Kind of looks like we have absolutely. If you look at a baseball or at a basketball, you will see hyperbolas on that baseball or basketball as the shape. Anybody see that it kind of looks like two parabolas too, right? Okay, and that axis of symmetry for each one would go through the foci, but if it had a directrix, that would be the line that it reflects across. Okay, so we're going to talk about hyperbolas today, and a hyperbola is defined as the set of all points x, y in a plane, the difference of whose distances from the two distinct points called foci is a positive constant. So when we talked about ellipses 2 days ago and yesterday, we didn't look at the difference between those two foci. We looked at the sum of the lengths of the two foci. And does anybody remember what the two foci lengths added up to? The major axis, exactly. This time, we're looking at the difference of those two. And the difference of those two is also going to be constant, just like the sum of the ellipses distances were. A transverse or focal axis is a line that passes through the center, the two vertices, and the two foci. So everybody's all in one nice, neat line. Okay? Here's a quick GeoGebra applet to show you how these guys work. And they've nicely labeled the foci, the vertices, the center. They call it a conjugate axis, that is the opposite axis that does not contain all of the parts. It only contains the center. But they call this the focal axis. Our book calls it the transverse axis. Okay? And watch what happens as I choose any point along this hyperbola. Notice how the difference between the two lengths is always 3.51. It doesn't matter where I go. And so that's kind of the gist of it. And then this was also going to be 3.51. It doesn't matter where I go on this one. Okay. All right, so let's see how this works. Standard form of a hyperbola. Again, we have a horizontal or a vertical transverse axis. Horizontal and vertical focal axis. What do you notice about the equations compared to ellipses? Very similar to ellipses. They have a minus. That's your most important distinctive difference. Okay? Instead of closing it in, it makes it push out. So notice the minus between. What else do you notice? The x and the y could potentially switch. So if it's going to be a vertical hyperbola, or have a vertical transverse or focal axis, the y squared will be positive. If it's going to be horizontal, the x minus h squared will be positive. And where is a squared at each time? Under the first, always with the positive one. Okay? So with ellipses, the a squared got to move around to be the biggest one no matter what, to make the major axis, right? This one is going to stay put and always be with the positive transversal axis. Okay, makes sense? Also, what do you notice about c squared? A squared plus b squared this time, right? What was it with ellipses? Minus. So when we have a minus in the middle, we're going to add. And when we have a plus in the middle, we'll be subtracting. Make sense? Because in order to keep the foci inside of an ellipse, we had to subtract or they would have been too big. And in order to make the foci be outside of the hyperbolas, we have to add to make them pop out. Does that make sense? All right, so then the other thing that we haven't talked about yet are these asymptotes. So remind me, what are asymptotes? We dash them because they're really not part of the graph, right? But they're lines that something is going to never touch, approach but never touch. Okay, so we have two asymptotes. One of them will be k plus or minus b over a times the quantity x minus h. The other will be k plus or minus a over b times the quantity x minus h. But don't worry so much about whether it's going to be a over b or b over a, because when we graph it, it's going to make sense. Okay? This looks like point slope form, doesn't it? Only they've moved the k over here. It's like y minus k is equal to our slope times x minus h. Okay? So it's going to be very similar. I don't care if you bring the k over or if you leave it with the y. I'll be okay either way. Okay? And our a, because it's underneath our positive one and is on the transverse or focal axis, is going to kind of spread things out. A in one direction, A in the other. B will go up and down in this case, that same distance. And then we can use this box. And this box is dashed because it's really not part of the graph either. We can use the box to find our asymptotes. The diagonals of our box will be the asymptotes that the hyperbolas approach but never ever touch. Make sense? Okay, so let's see it in play. So we'll start out with something fairly basic. This first hyperbola is x squared over 9 minus y squared over 25 equals 1. What's the center? The origin 0, 0. Okay, so we know the center is the 0, 0, the origin. And is this a vertical or a horizontal hyperbola? Horizontal because the x squared is positive. Okay, so a is always going to be, the a squared is always going to be underneath your positive one. So how many units are we moving from our center? And it's going to be 3 to the right and 3 to the left. And those are our vertices. Okay. So our vertices are at negative 3, 0 and positive 3, 0. Okay. How much are we moving up when we want to make our box? So we'll move up 5 from the center, down 5 from the center. But these are just points that are helping us figure out how big our box is. So we'll dash a box now that goes from the vertex down to 5, down to negative 5, over to 3, up to positive 5, and over again. So this is a dashed line. It's not really part of our hyperbola. And then we draw the diagonals. So we draw the diagonals. Those give us our asymptotes. Bless you. And so we know the appearance of our hyperbola now is going to approach those asymptotes but not touch them. And next we need to find the foci. So we know that a squared was 9, b squared is 25. So how do we find c squared? A squared plus b squared. So 9 plus 25 is 34, so C will be the square root of 34. Square root of 34 is just under 6, right? Square root of 36 would be 6. So from our center, we have to be careful, always from the center, we're going to move almost 6 out and almost 6 left. So the foci are inside of the branches. Does that make sense? Okay. Pushed away from the center. So our foci are negative 6, 0, and positive 6, 0. So all that's left is to talk about our asymptotes. Okay? I said don't stress about these because they're not bad, right? We put them in point slope form. It would be y minus its coordinate is equal to plus or minus our slope times x minus its coordinate. That's point slope form. Because we went 6 to the right. Sorry, not 6. I tried to do that. My fault. Square root of 34. Thank you for catching that. Talked about them, and then I decided to name them 6 instead. The plus or minus the square root of 34. All right, so looking at our lovely box that we've got here from the center, how much did we rise? And how much did we run? 3. So we have a plus or minus 5 thirds, because in this case, when we're going up and to the right, it's a positive 5/3 slope. But if we were going down and to the left for our other asymptote, that's a negative 5/3 slope. So we tighten it up and just say y equals plus or minus 5/3 x for our asymptotes. Questions about this one? All right, so next example. You love to complete the square? This is your problem. We have to complete the square in order to get this in the right form, the standard form, right? So let's gather our y's together. Gather our x's and take our 47 to the other side. Okay? What's the first step? Factor. Get that leading coefficient out of there. So if I factor 16 out, I will have a y squared, and dividing by 16 I get minus 4y. And what am I taking out of my... Thank you. Try to change the sign on me. All right, and this one? A negative x squared, or negative, not x squared, but negative 1, right? And when we do that, we'll have an x squared plus 2x. Looking ahead at the next one already. So now we need to complete our squares. What's going to make that first parenthesis a perfect square? Half of 4 is 2. 2 squared is 4. But we're not adding 4. What are we adding? 64. So the second parenthesis, what will make that a perfect square? 1, but we didn't actually add 1. We have to take away 1 to balance both sides of the equation. So now we have a perfect square trinomial that can be written as a binomial squared. Square root of the first, sine of the middle, square root of the last. Square root of the first, sine of the middle, square root of the last. And we add a negative 47 and a negative 1, we'll get a negative 48 plus 64 is good old 16. So last step, divide everybody by 16. Nothing wrong with holding that place and calling it y plus 2 quantity squared over a 1 minus x plus 1 quantity squared over 16 equals 1. So now that it's in standard form, what's the center? Careful with this one, just like our parabolas, things can move around. Everyone see why? The x is second, okay? So make a note on your paper to remember, watch out for moving h's and k's, right? Same thing with our parabola, we had to do that before. We were careful always to put the x squareds first in our ellipses and have a squared move around. With hyperbolas, because of this negative, sometimes that x is going to be negative. So our center is -1, -2. So we'll start out at -1, -2. Horizontal or vertical? Vertical y. The y is the positive. So we're moving up 1 and down 1 for our two vertices. So -1, 1 and -3, or sorry, -1, 1 and -1, -3. So foci. How do we find foci? Yep. There's a minus in the middle, so that makes the c squared equal a squared plus b squared. What's a? That's the 1. A squared's always beneath the positive term. And b squared is 16, so c will be the square root of 17. Okay? So we are moving the square root of 17 from the center up and down. A little bit more than 4. So it's just a little bit more than 4 up and a little bit more than 4 down from our center. Yep, square root of 17, square root of 16 is 4, so the square root of 17 will be a little bit more than that. And so our center, the x is not changing. So of the center, we keep the x the same, but it's the -2 that's having that positive, or the adding the square root of 17 and subtracting the square root of 17. So you can certainly leave it as plus or minus the square root of 17. And now we're ready for the asymptotes. So we have to plot B. To find B, we want to go 4 left and right, don't we, from the center. But those aren't actually part of the graph, they're just there to help us make our box. And make sure you do it from the vertex, not from the foci. Now draw your diagonals. Bless you. And it wants to have the foci be within the parabola or the hyperbolas. So we're opening up and down. And now we need to find the equation of those lines. So to find the equation of the lines, we're going to say how much are we rising and how much are we running. We went up 1 and over 4, right? So y minus its coordinate is equal to our slope plus or minus times x minus its coordinate. Make sense? And you can leave it like that as far as I'm concerned, or you can do it as the book suggests, which is y equals -2 plus or minus 1/4 times the quantity x plus 1. But I don't mind it being in point slope form. All right. Questions on this one? Next example. Standard form of a hyperbola, vertices at plus or minus 4, 0, foci at plus or minus 6, 0. So start by plotting your vertices. Based on that, what do you know? The center is what? Yep. So we also know not only the center, but which orientation it has, right? It is horizontal, so which is the squared term? I'm sorry, which is the positive squared term? The x squared. So we'll have an x squared over a squared plus a y squared minus a y squared over a b squared equals 1. What else do we know? The a is 4, so a squared is, what else do we know? What's c? Distance between, and that's where I wanted to say too, but it's not the distance between the vertex and the foci, it's the distance from the center to the foci. So c is 6. And with hyperbolas, our equation is c squared equals a squared plus b squared. So 16 plus b squared is 36. What's b? 20. b squared is 20. Square root of 20 is b. Okay. So now we need to find, we found the standard form. We're done. Okay. You can find the asymptotes if you want to, but I want to give you time to work on your assignment. Okay. So we got a couple more examples to go. Anybody have questions on this one? All right. Here comes the next. Find the standard form of the hyperbola if the vertices are 3, 4, or 3, 0 and 3, 4. And they give us asymptotes this time. So plotting the vertices, what do you know? It's vertical. So, and we know the center. What's the center? 3, 2. So because it's vertical, which is our positive the y. So we want to make sure that we do a y minus 2 squared over a squared minus x minus 3 squared over b squared is equal to 1. We know a is how far? 2. So our a squared will be 4. And since a is 2, what do you think b has to be? 3. Does that make sense? We're going to be rising 2 and running 3. To make our asymptotes. So b squared will be you could sketch your diagonals. And we could finish things off and find the foci and so forth, but save time and give you time to work. Everybody looks perplexed or lost. I think we're doing good. Okay? Questions on this one? All right, next example. Unfortunately, no. Good question, though. So it depends on who is in power, who's the positive. Okay? So it's not always going to be A over B. Sometimes it will be B over A. Exactly. You may have to double it or triple it or what have you. But yeah, you should know the other one. Actually, you should never have to double or triple it. It should be the other one. Makes sense? Unless it's been reduced like 2 over 2 or something like that. Okay? All right, good question. Any other questions? All right. Last example. Now we have a hyperbola that has vertices at 1, 2, and one at 1, negative 2. And it passes through the point 0, square root of 5. So what do we know first of all? We know the center is 1, 0. And we know A. And we know it's vertical, right? Apparently I liked vertical ones. We did more verticals than horizontals. I guess I got a 5. All right, so because it's vertical, which is squared, which is positive, the y. So we'll have a y minus 0 squared over a squared minus x minus 1 squared over b squared is equal to 1. And a is 2, so a always goes under the positive, under the first one, so we'll have a 4 there. So now all we need to do is figure out what b squared is. And the only thing they told us is that it goes through the point 0, square root of 5. So 0 over square root of 5 is a little bit more than 2. So we know it's going through this point. I can draw it actually going through the point. Well, the square root of 5 is a little bit more than 2, right? Because the square root of 4 is, so 2.2. Okay? So we're 2.2, 0 over 2.2 up. So how can we find out what b squared is? We don't know the foci. We don't have foci. we knew C, we could use that to find B, right? But they didn't tell us anything about C. But they told us one point that satisfies the equation, right? Yep, so plug it into the equation. So let's put 0 in everywhere we see x, and square root of 5 everywhere we see y. So the square root of 5 squared is, so we'll have 5/4 minus negative 1 squared is 1, so positive 1 over b squared, right? And since we're going to be dealing with fractions anyway, let's make our 1 into, have a common denominator of 4/4, right? So to solve this, we need to take that 5/4 to the other side. So we subtract 5/4 from both sides. We'll get what? 5/4, or negative 5/4 and a positive 4/4 is negative 1/4. So if a negative 1 over b squared is equal to a negative 1/4, what's b squared? 4. And b would be 2, right? And we need the 4 anyway. So we can rewrite this as y squared over 4 minus x minus 1 quantity squared over 4 equals 1. And that's all we were asking for, is what's the equation. Questions on this one? All right. Assignment. It's out of order, and that's okay. I did this intentionally. So start with 19 through 29 odd. It'll start you with some easier problems. And then go back and do 9, 13, and 17, because they're a little more tough. And then hit 39, 43, 45.